Good morning. I'm Gianluca Brilli from the University of Modena Reggio Emilia, and today I will present you our research work in collaboration with the University of L'Aquila in the context of AI for CSM and Fractal European projects. Commercial off-the-shelf heterogeneous systems integrate an increasing number of computing engines that share a lot of hardware resources. And the contention on these resources can imply unpredictability in terms of task execution time. Recent works proposed in literature show that a task can be slowed down up to 16 times compared to the case without interference when there are memory-intensive applications deployed on CPU cores and accelerators. Commercial off-the-shelf heterogeneous systems are not designed for real-time applications. However, they are often the preferred choice also for time-critical systems. Several works try to derive bounds on task execution time. However, it's very hard to derive accurate bounds since the hardware is too complex on commercial off-the-shelf systems, and working with safe bounds is too pessimistic. And this can imply decrease in terms of parallelism. For this reason, runtime bandwidth regulators are often the preferred choice to mitigate the memory interference problem on commercial off-the-shelf systems. And as we can see on the right, these regulators can be designed using a monitoring and throttling control loop. A monitoring and throttling control loop is composed of four main phases, where the most important are the monitoring of the bus and the analyze and plan phases, where the new regulation value is computed. And on the throttling phase, the new regulation value is applied on the bus. And to design a fine-grained bandwidth regulator, all these phases must be performed as fast as possible. And this can be achieved if the components used to implement the monitoring and throttling control loop are tightly coupled. Time-critical systems like automotive applications are typically composed of fine-grained tasks characterized with an end-to-end delay in the order of microseconds. And as we can see from the trace reported on the right, the bandwidth requirements of a real-time operating system can change very quickly. And for this reason, to cope with these ultra-fine-grained bandwidth granularities is crucial to close the monitoring and throttling control loop as fast as possible. In the next slides, I will discuss some approaches to design monitoring and throttling control loops targeting FPGA-based heterogeneous systems. FPGA-based accelerators typically adhere to a standard template where traditional multi-core CPUs, also called QoS CPUs, are coupled with application-specific accelerators. And let's see more in details the main components of the accelerator clusters. So in addition of the accelerator data path and the local memory, there is a DMA engine that is an interface between the local and the main memory and can perform memory transactions using a very high memory bandwidth. There is also a soft core, also called the proxy core in our publication, that can control the entire cluster. And controlling the accelerator cluster using a soft core is more flexible compared to use a traditional finished-state machine. And for this reason, a lot of works available in literature use this template. The first approach that we considered to design a monitoring and throttling control loop represents the case where there is no available hardware support for bandwidth regulation on the target platform. The regulator is a piece of software, a small control firmware that executes on top of the soft core inside the accelerator cluster. The monitoring is performed using a Xilinx Axi Performance Monitor, which is a small monitor instantiated on the FPGA, so inside the cluster. And the throttling is implemented by splitting a memory transaction into a certain number of sub-requests and interleaving these requests with a configurable idle time. The main drawback of this approach is due to the overheads needed to reprogramming the DMA by the soft core. And this overhead grows very quickly by refining the granularity of the bandwidth regulation, as we can see on the right. And this is an example of a loosely coupled monitoring and throttling control loop. Then we considered the case where the target already has available hardware components dedicated for monitoring and throttling. In this case, the regulation firmware runs on top of an ARM Cortex-R5 outside the accelerator cluster. And to implement the monitoring phase, we used an hardware axis performance monitor, which is a monitor already integrated by Xilinx directly in the memory controller of their platforms. For the throttling phase, we used the ARM QoS 400, which is a fine-grained regulator already available on QoS platforms. And also in this case, the monitoring and throttling control loop is loosely coupled. The goal of our work is to make the monitoring and throttling control loop as tight as possible, targeting FPGA-based heterogeneous systems. The proposed runtime bandwidth regulator, which is called RBR in the rest of the presentation, can be easily integrated inside a generic accelerator cluster, as the one that I introduced before. Our RBR is a custom-made IP that can be controlled by the soft core that monitors the DMA activity and regulates the cluster memory bandwidth by implementing a tightly coupled monitoring and throttling control loop. The memory bandwidth regulation is achieved by interleaving transactions with a configurable idle time, which is regulated by our RBR. And let's see more in details the main components of our bandwidth regulator. So given a memory transaction T and a throttling factor THR, there are two different phases, where the phase one is the monitoring activity, that when a certain amount of bytes have been copied by the DMA, which is regulated by a threshold parameter, the monitor sends the time needed to perform the memory transaction, which is the copy cycles parameter, to the throttler. Then the throttling phase can start, where the throttler computes the amount of idle cycles to apply on the bus using the following formula that is based on the monitoring activity and the throttling factor THR, which is an input of the RBR. Let's see a simple example. Suppose that the blue interval is the active time. When the transaction ends, the copy cycles measured by the monitor is sent to the throttler. The throttler computes the idle cycles and apply that amount of idle cycles to the bus, which is represented by the black interval. Then this procedure repeats for all the parts of the main memory transaction. And this is an example of a 50% bandwidth regulation. Our RBR does not introduce significant overheads and implements a tightly coupled monitoring and throttling control loop. In the next part of the presentation, I will discuss our experimental results, where in the first one, we propose an assessment of the benefits that we achieved using our tightly coupled regulator against three different loosely coupled solutions. While in the second one, we applied our regulator in a real scenario where the target is a system-wide interference mitigation. Before presenting the results, I have to introduce some general acronyms that are LCMT and TCMT, that stand for loosely coupled monitoring and throttling and tightly coupled monitoring and throttling. The evaluated loosely coupled solutions are referred as LCMT software DMA and LCMT QoS 400, which are the two approaches that I introduced before. Then there is also the LCMT RBR, which is an hybrid version of the two, which is composed of an hardware APM and our FPGA-based throttler. To evaluate the 4 different regulators, let's consider a sequence of bandwidth requirements that arrive from a memory scheduler at fixed times that are T1, T2, and Tn, with a given period t expressed in microseconds. On the left, we can see a graphical representation of the input, where on the x-axis we have the timestamps. The trace are the bandwidth requirements, and on the y-axis we have the bandwidth request expressed as percentage of maximum memory bandwidth that can be used by a single cluster. Then for each bandwidth regulator, we measure the minimum regulation granularity, which is given by the monitoring and regulation overheads. And this granularity is reported on the table that shows the minimum period t supported by each design, which means that for each design, the bandwidth request cannot be faster than these precise values. And for example, considering the LCMT RBR, if the bandwidth requirements arrives faster than 192 microseconds, that regulator will fail to provide an accurate bandwidth regulation. Then, by comparing these 4 solutions, we derive that our TCMT is 6 times faster than LCMT RBR, 10 times faster than LCMT QoS400, and more than 100 times faster than LCMT software DNA. In the last experiment, we evaluated the effectiveness of our solution to provide a system-wide interference mitigation. And we compared against the typical usage of the QoS-based ecosystem of the Zinc UltraScale Plus, where the goal is to control the memory interference of different applications. There are 2 tasks deployed on the APU, 2 more tasks deployed on the RPU, and 2 clusters deployed on the FPGA with an RBR connected. The constraint is that all the tasks must meet a given QoS requirement, and this experimental setup was proposed by the researchers of the Barcelona Supercomputing Center in their SCRTS publication. In the table on the right, we can see the results, where the columns are the QoS requirements, which are the maximum tolerated slowdowns. And we evaluated 20, 40, and 60%. For example, a 40% means that each task can tolerate a 40% increase in their execution time at most. And from this table, we can see that the 40 and 60% maximum slowdowns are feasible configurations using our tightly coupled solution, while these 2 configurations are not feasible using loosely coupled regulators, as shown by this reference. To conclude this talk, we presented a tightly coupled bandwidth regulator targeting FPGA-based heterogeneous systems that allows to handle a microsecond scale bandwidth race. Our design is platform independent and general enough to be deployed on a generic accelerator cluster. And our RBR is up to 100 times faster than loosely coupled solutions and also more effective in mitigating memory interference compared to available QoS-based solutions. Thank you for your attention.